Let me introduce our first speaker today, and his name is Viktor Kira. Viktor is a principal engineer at Kaffion, technical lead on the advanced installer team, and a Microsoft MVP. When he's not pestering his colleagues about modern C++ style, he likes to build tools that improve developer workflows, and he also frequently uses his alma mater, his university, which is the University of Craiova in Romania, and there he teaches students algorithms. And his talk today is called A Short Lifespan for a Regular Mess. Let's have a big hand for Viktor Kira.
Okay. Thank you. Are we on? Yeah. So welcome everybody. Thank you for coming. I'm glad some of you are still here after last night's party. So let's get started. Today we're going to talk about regular types. We're going to do a case study on span. We're going to see some problems that may arise when designing types, and we're going to see some mistakes that have been made along the way by very smart people. And we'll see what we can learn from all of this. Who has seen any of my previous talks on regular types? I see some hands. OK. So we will start by doing a short intro and overview of the theoretical principles behind regular type design and why this is important when designing types and when consuming library facilities, for example, the standard template library in C++. So this talk is not just about regular types. It's actually a moment to reflect on STL and its design principles as they were stated by Alexander Stepanov in his now 21-year-old paper on fundamentals of generic programming. We shall see that regular types naturally appear as necessary foundational concepts and building blocks when we try to investigate the requirements that we need to impose on types when we're using algorithms and Stl data structures. But we're not going to talk just about regular types. We're going to talk about values, about objects, not as in object-oriented programming, or rather as objects residing in computer memory, about concepts, about ordering relations, and we shall see that there are tricky bits there, about requirements on types, about equality, and we're going to see that defining equality is not as easy as one might think, whole part semantics, about object lifetimes. We're going to use span as a premier example from C++ 20. We're going to talk about C++ core guidelines, C++ 17, 20, and things coming up next. So there's lots of things to cover, and we're going to pick just certain parts of each of those topics and analyze some aspects that are relevant to this discussion. I do recommend that you watch this talk by Titus Winters from CPPCon. I'm guessing some of you already seen it. It's about type properties and type families and how we can properly describe the properties of types and how we can build type hierarchies and do overloads properly for our functions and our APIs. But let's start with the beginning, like 2,000 years BC. And we're going to take an algorithmic journey, and I do recommend this fantastic series of lectures by Alexander Stepanov that he gave at A9. It's basically a story that follows 4,000 years of mathematics, starting with ancient Egyptians and Egyptian multiplication and GCD, and following the mathematical evolution and human understanding of logic and mathematical constructs, and how we've refined these formalisms to properly describe properties of types and numbers. So there's a lot to cover there. lot of hours of video, but for those of you who are mathematically inclined, it's a very interesting journey. A shorter version of that would be this book, again by Alexander Stepanov and Daniel Rose, From the Mathematics to Generic Programming, and it's the same journey with implementations, theorems, lemmas, proofs, mathematical histories, tidbits, and it's a very enjoyable story to follow. It's one of my favorite books. I had to put it in there. But in the beginning, there was just zeros and ones. And we need to define a common vocabulary so we can properly discuss these concepts. And I'm going to give a brief definition of these terms from elements of programming. So a datum is a series of zeros and ones, and they can represent anything. They have no meaning. A value type is the correspondence between a species and a set of datums. A value is a datum together with its interpretation function. For example, 32-bit integers in big endian representation is a value. And most importantly, and not everybody gets this, values cannot change. Values are immutable. The number 5 cannot change. So when we talk about value types and equality, if a value is uniquely represented, because a value can be represented differently in computer memory, then equality implies representational equality. That seems obvious. If a value type is not ambiguous, representation equality means equality, if we define it properly. So an object is a representation of a concrete entity as a value in computer memory, given by its address and length. An object has a state that is the value of that type. And of course, the state of an object can change in memory. So this is what people usually think about when they think about values. These are objects in computer memory. A type is a set of values that share the same interpretation function that operates on those values. And a concept is a collection of similar types. Everything I just described is from Elements of Programming. If you don't have this book, you really should. I consider it a fundamental book for our science. It's not an easy book. It's the kind of book that you keep on your desk and keep reading from it. It's available in PDF format, and it's free from the official website there. Or you can, I think you can still order it from Amazon, but it's not in reprint anymore. So mathematics really does matter, I claim. And another very less known video by Alexander Stepanov from Smart Friends U describes the Gcd algorithm and its evolution over 2,000 years. And it's a very interesting refinement of this algorithm with implementation details. And I do think some of you will find it very, very entertaining. But you may say, I've been programming for many years now, and I didn't need any mathematics to do that. I'll be just fine, thank you. I don't need this nonsense. Well, first of all, I don't really believe you. And the reason that things just worked for you is because others have thought long and hard to design libraries that feel natural and intuitive to you. So you may not have consciously thought about that, but you were unconsciously consuming concepts defined by others. And we shall see that if you break those assumptions, you will have surprises when using these facilities. So 4,000 years of mathematics leads up to fundamentals of generic programming, the thing we started with. And I'm going to just lift some important quotes from this paper, because I know not all of you will be inclined to read it. It's not a long paper, though. Generic programming depends on the composition of programs into components which may be developed separately, combined arbitrarily, subject only to well-defined interfaces. And I think this pretty much defines programming as a discipline, regardless of the programming language you choose. Among the interfaces of interest, the most pervasively and unconsciously used are the fundamental operations common to all built-in types, like numbers, that extend to user-defined types, like copy constructors and assignment and equality. So we shall see that we have to meet the expectations of the user when defining our own types, so that they don't behave strange. Equality means equality. We must investigate the relations which must hold among these operations to preserve consistency with their semantics. So we don't want to define an ordering relation which does not make sense if we model something from the real world. In other words, we want a foundation powerful enough to support any sophisticated programming tasks, but simple and intuitive to reason about. Is simplicity a good goal? Are we C++ programmers or not? Well, I really hate it when C++ programmers brag about being able to grok and understand some obscure language syntax or some really, really clever template tricks. I do claim that simplicity is important for all of us. And being able to reason about a piece of code, whether you're an expert or a beginner, is a sign of proper design. We should not be proud to understand really clever stuff. Stuff should be simple. If reading the original 21-year-old paper by Alexander Stepanov might prove a little bit tedious for some of you, I do recommend a more recent take on that. Again, by Titus Winters. It's a relatively short article on the AppSale blog on revisiting regular types. And basically, it's the most recent take on the original Alexander Stepanov paper. And it evokes the Anna Karenina principle for designing C++ types, in the sense that good types are all alike. Every poorly designed type is poorly designed in its own way, its own unique way. So there are horrible stories there. So it's a very interesting article. I do recommend that you read it. And it does cover newer concepts in the language and in the library. So it's a very fresh take on regular types. If you're interested, I do recommend that you start with this one and then go to the original Stepanov paper. So it examines how regular type design affects non-value types, because for value types, it seems like it's almost seamless, and provides the basis to discussions about newer additions to the library, like string view and span, and how we can use them and leverage this functionality without disregarding completely regular type design. But let's go back to the roots, STL and its design principles. I think this is the first still available recording of stating the manifesto or the design principles of STL. It's from the early 2000s, a lecture by Alexander Stepanov. It's a bit lengthier, but I think it's full of interesting details that you might not know of. Just a little small things I draw from that lecture. STL is about systematically identifying and organizing useful algorithms in data structures. This seems obvious now. It wasn't over 20 years ago. Finding the most general representation of algorithms, using whole part object semantics for data structures, using abstractions of addresses, you know about iterators, now we're going to have ranges, as a glue between algorithms and data structures that we're using. And algorithms are associated with a set of common properties of types and operations. For example, if we take addition, multiplication, min, or max, these are all associative operations, so we can reorder operands, and hence we can parallelize the operations, and we can use algorithms such as accumulate or transform reduce, or basically parallelize and reduce the operations for any operation that's associative like this. So this is a natural extension of 4,000 years of mathematics, like I said. And a fundamental insight is that there is an algorithm behind every while and for loop. We've heard that many times by now, but this is at the core of STL. STL data structures extend the semantics of C structures as in terms of layout in memory. They don't behave differently. Two objects should never intersect. They are separate entities, and they should have separate lifetimes. This is the thing that we usually don't respect when designing types, and we do have intricacies and weird relationships between our types and our understanding when we're analyzing a complex system in terms of lifespan and how objects relate to each other. It's all very often very difficult because we forget about this thing, and we design very complex relationships within our objects. We should try not to do that. It's not always easy, but when you copy the whole, you copy its parts, whole part semantics. When the whole is destroyed, all parts should be destroyed. Think about remote parts now. Think about how we design structures that have pointers to other things. So we often break this rule. And two things should be equal if they have the same number of parts and their corresponding parts are equal. This one seems obvious. Again, it's not something that we do regularly. Generic programming does have its drawbacks. You rarely have some extraction penalty. You have the implementation in the interface because we're talking about templates. We have early binding, horrible error messages like we all know, duck typing, and unexpected results down the line. Things might work now for the types we're using today and might break in the future when we're introducing new types into the mix. So we need to fully specify requirements on types in order to make sure that the algorithms we provide work with the types we intended, not by chance. We don't want duck typing. Some examples of named requirements are here on the screen. There are lots more of them. I just picked some more frequent ones, and we're going to focus on a few of them. Named requirements are used in the normative text of the C++ standard to define expectations of the standard library, so that you know if you're using the sort algorithm, what's the expectations, for example, for the type you're sorting in some particular collection, or for the predicate you provide, if you provide a custom predicate for your sort algorithms. So some of these requirements are being formalized as C++20 concepts. But until then, until you're on C++20, and even then, the burden is on us to ensure that library templates are instantiated with the proper types, and that we know what we're doing. Yeah, with concepts, we're going to get better diagnostics when compiling and misusing a particular algorithm. But again, we need to understand why we're getting that diagnostic. It might be prettier, but we still have to understand why we have that requirement. So what is a concept anyway? It's a formal specification that allows us to verify that the template arguments provided meet the expectations of the template during overload resolution and template specialization, not within the template body when the code is actually used. So each concept is basically a predicate that is evaluated at compile time, and it's part of the interface of that function template. Some examples, again, of concepts from C++20. Right now, I'm going to just rant. It was relatively recently, it was decided to switch to snake case notation, so lowercase snake case notation for concepts. I personally prefer the Pascal case, and I'm going to tell you why. So I think people just lack imagination here. I like the original Pascal notation that has been in the proposal for many years now, because I think as a new thing and a very strange idea, for C++, concepts need to stand out. They are policies rather than types. And because they're not types, I don't think they should be easily confused with standard types that use the snake case notation. And I think consistency with template parameters, as they're usually used by everybody in Pascal notation, is again desirable, because they're going to come in as replacements for those specific types or type names. So, for example, this is how we defined a basic string. And the most awful thing, I think, is the confusion with type traits. We have here an example of a type trait and a concept, and I dare you to tell me which one is which. And they don't mean the exact same thing. This is the most weird thing. Okay, so end of rant there. So what's the practical upside? If I'm not a library developer, why do I care? Well, for sure you're using, or I hope you do, Stl algorithms and data structures. So designing and exposing your own vocabulary types when you design a library or when you provide an interface for some functionality that you implement, again, you need to meet the expectations of the programmers that are consuming those things you're designing. They should behave like the other libraries that they've seen, and the most prominent one is the Stl. So if you're designing something that behaves very strangely or very differently from Stl, then people are going to have surprises. Let's pick on one example, the compare concept, and I'm going to pick the sort algorithm because it's the most frequently used, I think. What are the requirements of the compare type? So the compare is basically a function object that is a predicate because it returns a Boolean value, and it's a binary predicate because it takes 2 parameters. Pretty simple. It should look like that. But what kind of ordering relation is needed for elements of the collection in order for this kind of predicate to work with the sort algorithm? So I do have a whole talk where I analyze this in depth, and the gotchas required, the gotchas attached to this problem when defining a proper ordering for a compare concept. Bottom line is we need strict weak ordering. The Stl expects that from our types. And these would be the axioms that guarantee that we're not violating this requirement of strict weak ordering. And I'm going to draw your attention to the equivalence relations. The equivalence relations is when we cannot say if A goes before B or B goes before A. In that situation, we're saying that it's an equivalence relation with regards to those values. Less than the comparable is a particular instance of strict weak ordering where the operation is less than. That's just it. I just replaced generic comparator with less than. And again, we have the equivalence relation. Named requirements. We're going to focus now on EqualityComparable concept. As defined, semiregular is something that is default constructible, movable or copyable, move assignable or copy assignable, swappable, and destructible. Most types kind of fell into this category. And regular, as in defined in elements of programming, is a semi-regular type that is equality comparable. And we shall see what that implies. Stl assumes equality is always defined, or at least an equivalence relations, like we saw when we presented the axioms. So Stl algorithms assume regular types. Stl containers assume regular types are stored in them. And it was clearly designed with regularity as its basis. So if we do not understand these concepts, we're not going to be able to use it properly. Equality comparable is defined by 3 axioms: reflexivity, symmetry, and transitivity. This is something we learned early on in school. And types must provide an equality operator, and it should have standard semantics. We don't want to change the meaning of equality for our type. We cannot make it mean something else. And for types that are both equality comparable and less than comparable, STL makes a distinction between equality and equivalence, and it's sometimes subtle. And we sometimes do weird things around this area. Of course, equality is just a special case of equivalence. And this is how it should be defined. Defining equality is really, really hard. Doesn't seem so, but it is. I'm going to quote again Stepanov. Two objects are equal if their corresponding parts are equal, applied recursively, including remote parts, but not comparing their addresses, excluding inessential components, and excluding components which identify related objects. Phew. And this is not a complete definition. So, weird corner cases everywhere. I have to point out the new addition to the C++ standard, the three-way comparison, because it's related to what we discussed, ordering relations. And we have the so-called Spaceship Operator, and that defines basically ordering relations between values of types. And we have several ordering categories or ways of defining the strength of the relationship, of the ordering relation. I don't have time to go into details, but I'm going to point you to a very good talk about that. And we have a contention here in defining this operator for types, or even for library types, because we want the convenience of this operator, so we don't want to write 6 different operators, less than, greater than, less than, equal than. And at the same time, we have the problem of implementing this efficiently for wrapper types, like the example I'm pointing out here. So if we have like a member that is a collection, and there's this contention about doing equality comparison efficiently and doing implementing the three-way comparison generically. So we might need to split this implementation into a generic comparison and treat equality and respectively inequality separately, just to preserve efficiency. So there's a tension there. The mothership has landed. This operator has been implemented throughout the STL. So we're going to get it for most of the data structures in the standard library. And this is the talk I referenced earlier. If you want to learn more about three-way comparison, I'd recommend this talk by Jonathan Müller. It's a very recent one, so it's very relevant still, because this design was in evolution. But before we get too far with C++20 stuff, let's examine a bit an interesting C++17 type. I think this one is much more familiar to many of you. String view is an object that can refer to a constant continuous sequence of char-like objects. And it does not manage its storage. The storage is up to the user. Again, I have a whole talk just about string view and gotchas and best practices in using it and what it entails and what can you do with tooling to help you there. I'm going to just summarize some of the important bits here because they're relevant to discussion further on when we tackle span. String view is a borrow type. I think Arthur borrowed this term from the Rust community, where they have the borrow checker for ownership checking. And string view succeeds admirably at the goal. It was designed for this, to be a drop-in replacement for a constraint graph. And the problem here is that this is the first mainstream borrow type in the standard library. So this is why it's attractive to many programmers. So that's why we need to pay attention to it and understand how to use it properly. Up until now, we had value types and reference types, and we knew how to deal with those. This is a weirder, new kind of type. That's why we have this term for it, borrow type. It's it wants to look like a value, but it behaves like a reference. So it's a strange thing. So it's essentially a borrowed reference to an existing object. They lack ownership. They should be short-lived. All borrowed types should be short-lived. They can generally do without an assignment operator, but we shall see that it's not always the case, like it's for string view. They generally appear only in function parameters list, and this should be the takeaway. This would be the safest point to use them. And they cannot be safely stored in data structures or returned from functions. So you have to be very careful there. But string view is assignable, so you can do that because it's convenient. But assignment has shallow semantics. So this works because the underlying strings are immutable, so they cannot change from under you. Meanwhile, comparison, because we talked about equality earlier, comparison has deep semantics, because when we're comparing two strings, we want the lexicographic compare of the underlying buffer that we're seeing through this string view. So again, we have to be careful here. But things work because the underlying thing is immutable. So when the underlying data or buffer is extant, alive, and constant, we can determine whether the usage we're seeing looks regular. When used properly, and this would be the recommendation, in function parameters, string view works well as if it's a regular type. It's obviously not a regular type as per the Stepanov definition, but it kind of behaves well when used in this restricted context. So it's safe and it's convenient. I wouldn't discourage people from using it. It's definitely efficient. So not great, not terrible, but we shall see that things get worse with span. So I'll give you C++20 span, which is a very confusing type and has been the subject of discussion for many months now, maybe years, within the C++ committee. Think of it as in array view, just like string view is, but the underlying data is mutable. It's not constant like it was with string view. This is necessary by design because its intent was to be a replacement for doing pointer arithmetic and basically traversing buffers that we need to change with pointers. So again, it does not manage the storage it refers to. Lifetime management is up to the user. It stems from the C++ core guidelines. So the origin would be in that original manifesto. There are particularly two entries in the CPP core guidelines referring to span. Use span to designate a half-often sequence, and I put links there. I'm going to provide slides right after the talk, so I have plenty of links and references in my slide deck. For those of you who want to dig further on, everything blue there is navigatable. And the bound safety profile, when we can check out-of-bounds accesses. Very briefly, informal non-explicit ranges are sources of errors. We all know that. We've all bumped into those. Ranges are extremely frequent. We always deal with ranges by pointer and length or pair of iterators or something like that, or two pointers. But they're typically implicit, and their correct usage is very hard to ensure. It's not built into some type. It's a convention that we pass a pair of things, and they mean a range, like a pointer and length, or two pointers, or pointer and something that we know it ends with a null, or something like that for strings, for example. So it's generally impossible to know if there really are said elements after the address we provide for the beginning of that range. So this is why encoding this information explicitly in a type is useful. But again, span is not bounds checked. So standard span comes from the GLCell or the guideline support library from the GSL span. And its purpose is to codify this information about range. and to be efficient. We don't want a high-level abstraction that costs something, because if we design such a thing, people are not going to use it. They're still going to use pointer arithmetic. So we want something that is efficient. Bound safety profile, indexing arrays using constant expressions, no array to pointer decay, the usual stuff we run into. And right, the gist of it is be explicit, use span. Again, some links to dig into with more examples and details there. So I mentioned the GSL. It introduced span, string span, and owner types. We now recognize those as string view and span. So it's an older design. So from the original paper, now we're going to focus on the span proposal, as it's going to land in C++20. The standard span comes directly from the GSL and is intended as a replacement for unsafe pointer and length parameter pairs. And this is the important bit. We expect it to be pervasively used as a vocabulary type for function parameters in particular. So its intent is to see this everywhere you used to see pointer and length kind of things. So this is why we need to be careful, because if we start sprinkling span all over the place, and we don't know the gotchas and how to use it, then we're going to have surprises, because it's not really bounds checked. So I have a link there to the original paper. We do have some tooling to help with this. We have CPP coordinate checkers in Visual Studio 2017 and 2019. And I think even 2015, there's a NuGet package that you can apply to check for these things and see recommendations. We have LLVM Clang Tidy that has a whole module on CPP core guidelines and checks and recommends such replacements, like the bound safety profile and recommending using span for encoding explicit ranges. These would be the checks from Clang Tidy and the details therein. This is how it would look like in Visual Studio. We have the two errors that we may see, two warnings that we may see: no array to pointer decay, and don't use pointer arithmetic. Very simple, trivial example there, and you even have a way to suppressing this locally if you don't want to be pestered about this. I'm not a fan of this usage, but you can suppress it locally if you want to enable that throughout your project. And this would be the experience you would have. You would start to get suggestions when you're trying to do pointer arithmetic things, and you're going to get suggestions to use span in such places to move the sliding window through your buffer. So this would be the experience you have. As you type or as you browse through code, you're going to see some of these tips. Whether you like to change something or not, it's up to you. Again, pointer arithmetic, use span. Some people don't like this, up to you. So span is defined as a pointer and a size, and can have either static extent or dynamic extent, depending on how you plan to use it. And you can construct span in various different ways, and I updated this slide because the information on CPP reference is not up to date yet. I updated this slide with the changes from Belfast, the last committee meeting in November. Now you have a range constructor for span, and yeah, this was the change from Belfast. You can construct it from a range. So we can construct it from an array, from a standard vector, the way we would expect to construct it. It has some convenient functions like front, back, and index operator and data. Has convenient methods to get the contents, the buffer as bytes. It's debatable whether this is too convenient. some people don't like the fact that this encourages this reinterpretation of the underlying buffer to bytes. The usual suspects, just as with string view, we had convenience things. With span, we have first, last elements. We can get a subspan, so we can narrow the view into our buffer. And there have been usability improvements in standard span from its original design, and it was refined throughout the versions of Clang was the earliest implementer of this library facility, and from Clang 7, 8, and 9, and now 10, span has evolved in libc++, following the evolution of the paper in the standard, in the soon-to-be standard. So we added front and back functions to improve consistency with standard library containers, like vector. Empty method was marked as no discard, just as it is with vector. We lost this operator in parens. This was like leftover in the original design, because initially it was intended to be a multi-dimensional thing, this array view. We now split this proposal. We have a separate proposal for multi-dimensional arrays, and that's going to land in the future, maybe C++23. We have structured binding support for fixed size spans. And now we have to think about what would Stepanov do if he were to design a span. And I think a very, very nice and very succinct paper from Tony Van Aert on should span be regular. And it's an amusing paper to follow, but it has some really deep nuggets of knowledge in there, and it does make references to elements of programming, so I liked it. And it talks about overloading operators can be dangerous when you change the common meaning of the operator. We already mentioned that at the very beginning of the talk. The meaning of copy construction and copy assignment is to copy the value of the object. And remember our definition of the value. The meaning of equality and less than is to compare the value of the object. Copy, assignment, and equality are expected to go together, just as with built-in types, with integers. Yeah? If we assign something, we expect, when we compare it, to be equal to that thing we assigned it to. And when designing a class type, where possible, we should strive to make it a regular type. Let's see how this applies to span. Copy operator is shallow, because it just copies the pointer and size within the span. We could make the equality comparator be deep, in terms that it compares the underlying buffer or the elements with standard equal, and just like string view does. We mentioned that string view does lexicographic compare when we do equality on string views. And the initial implementation, the very first implementation in the first draft of the paper was actually this, applying standard equal. It's not anymore. We shall see why. However, string view can't modify the element it points to, because the underlying buffer is immutable. So shallow copy for string view would be like a copy on write optimization. So it kind of works for string view, this shallow copy, just as it worked for many years with copy on write string implementations. But is span really a value? Do we need deep compare for spans? Span is trying to act like a collection of elements over which it spans. So if we construct a span from a vector, for example, it kind of wants to behave like the vector it spans over. But it really isn't behaving that way. It's definitely not regular. Basically, span has reference semantics. Maybe it's debatable if we should call it span ref, but we dropped that long ago. So deep equality implies deep const, logical const. as to extend this protection to the underlying data. So whenever we do deep equality comparison, we also want to be consistent and have deep constants. And span cannot guarantee that. All parts of the type that constitute its value, that is, all the parts that we copy when we defined a copy operator, must participate in equality so that we have a consistency. After we assign, we can compare for equality. Deep equality means the value of the span are the elements it spans, not what it's defined in, like the pointer and size. So deep equality would mean that the span, it's not the pointer and size that it's in its data structure. And it would mean that the components are the things we construct it from. But it's hard to tie the span to the original elements because those elements can change, and span has no way of tracking that. So if you want span to act like a lightweight representation of the elements it refers to, we need shallow equality, just like we have for smart pointers when we compare to unique pointers or shared pointers, for example. But shallow const implies shallow equality. So shallow equality might be really confusing. For example, if you're using string view right now, because you can, this might be really, really confusing because it behaves in a certain way for string view. And in your mind, if you take this parallel between string view and span, you think this is for strings, this is for generic buffers. You might be confused because the equality might behave totally differently for string view and span. So ultimately, the decision, because we couldn't settle as a community on a right answer here, ultimately, I think the best decision was to actually remove the equality operator from span. So rather than being confusing, it's at least honest. It does not define an equality. So it's definitely not regular. So it's a strange beast. So users of the STL can reasonably expect to use span as a drop-in replacement for standard array or standard vector in cases where it's appropriate and they want efficiency. They don't want to copy vectors for a particular operation if they're visiting those elements. And most of the time, it just behaves that way until of course, you try to copy or change its value. So then it stops meeting your expectations there. So it's definitely not regular. It's semi-regular. So it's a strange beast. There's an interesting article by Corentin Jabot. It's an older one, but it's still relevant about span. So non-owning reference types like string view or span, for these kinds of things, you need contextual information to reason about instances of such types. For example, when you're doing a code review, it's not enough to analyze just the diff, just the local usage. You have to understand where the data comes from, what it's bind to understand the extent of these types, like string view and span. So things you need to consider: shallow copy, shallow deep compare, const mutability, equality operator, things we discussed and things we saw from the Tony Van Aert paper. So these types, they have reference semantics, clearly, but without the magic that can make references safer. For example, lifetime extension that const references provide, for example. Think about const reference to string. Let's see a very short example here. For example, we have a function that returns a temporary string, and we bind it to a const string reference. We've seen this pattern for many years now. This is the C++ 98 thing to do. And this extends the lifetime of the temporary string returned by the function in the lexical scope of that reference, S. If we do the same thing with a string view, ouch. String view does not extend the lifetime of the temporary here. And the weird thing is, yes, you don't get a compilation error, but even worse, it might actually work because if that string implementation has, most string implementations have more string optimization, then it might actually work. So you might uncover a crash here when the string gets longer. So be very careful about this kind of usage. We do have tooling to help in this regard. So we're not just relying on the compiler itself. So it's good that we have additional tooling, but we do have to remember to use it if we're in doubt, or to use it regularly, and then we see misusages. There's a bug-prone dangling handle, clang tidy check, and checks for such dangling references to temporaries. It's even configurable. You can provide configuration options for other handle classes that you might have in your code base, things that behave like string view here. The default is for string view. And you can even plug in span there. Check that it behaves the same way, detect the same patterns. So we also have the lifetime profile. The original paper by Herb Sutter is linked here below. We have this in CPP core guidelines, and the gist of this paper is that it's important to prevent common dangling, because types like we have very natural conversions from string to string view, from vector to span, and using it irresponsibly, you almost guarantee dangling references. So that's why we need to get educated and understand the gotchas, and that's why we need to have tooling that helps diagnose these kind of issues. We had, for over a year now, I think, an experimental flag in Clang that would detect such usage and issue an error here, or a warning, I don't remember exactly. And tell you that, for example, SV is invalidated when the temporary is destroyed on line A. And recently, in Clang 10 or Clang trunk, we have default built-in diagnostic for this. The warning issued is dangling GSL. And it tells us the exact same thing, but in a nicer diagnostic. It tells us that object backing the pointer will be destroyed at the end of the full expression. And the end of the full expression is this semicolon here. So that's why we get warned. And it's nice that we have this built in now. We don't have to rely on static analysis or Clang tidy check. I'm hoping to see this kind of thing in more compilers, turned on by default. And what I'm hoping is to see such a thing extended for span as well. My understanding is that it's a work in progress, and we should expect to see this sometime in the future for span as well. So, simple rules for borrow types. They must appear only as function parameters or loop control variables. If you really must make an exception and return such a view, like a string view or a span, the function may use a borrow type to return it, but I would encourage you to properly annotate this, document this behavior, so that the caller of that function knows what to expect, and if he should take care of the underlying buffer or take ownership or something. So you definitely don't need to store these. So avoid storing these kind of borrow types in your data structures. So be explicit. You can play around with custom attributes. You can actually do this. The compilers will take anything there. So anything you can do to draw attention to unusual patterns, unusual behavior, like returning such views, like span and string view, anything you can do, it will help your callers. Unfortunately, you cannot enforce it so that they get a compilation error until we get things like the GSL dangling diagnostics that we have in Clang trunk right now. So be creative. What about compiler support for span? So I don't know if you know this, but there is a conformance view, compiler conformance view in Compiler Explorer. And as of November, I updated this slide. these are the compilers that have span included. And I'm going to mention that for if you're using Clang, only libc++ has span. It was the early adopter. libstandard C++ from GCC does not have span yet. So this is the up-to-date conformance. This would be the evolution. If you were an early adopter, from Clang 7, you had span, like bleeding edge stuff. And this is how it evolved through the specification, how the specification evolved. Very recently, in the Belfast committee meeting in November, we got a range constructor for span. I have shown that in the CPP reference screenshot where I updated it. We didn't get it for string view yet. And there's even a proposal, I'm not exactly sure on the state of that one, to use span of characters as stream replacement. So there's work in progress for span, and span-like things, so you should expect more. If you cannot wait and want an implementation of standard span that matches the current draft of the C++20 standard, and your tooling is not yet shipping such a thing, so if you're using Clang 9, you're good. Alternatively, you can use an open source implementation. My favorite is the one here by Tristan Brindle. It's on GitHub. There is even an implementation of span in the Chromium open source project, and that one is actually bounds checked. I'm not sure if it's configurable. But there are problems. It's not straightforward, at least not if you want a uniform usage. So you're guessing I'm talking about span here as the 5 phases of joy, because it lacks a feature test macro. I don't know how many of you have used feature test macros for other types, for other functionality in STL. But because it lacks a feature test macro, and to see if you actually have that implementation in your toolchain, you cannot use hasInclude for that to check whether you have the span header or not, because most implementations, for example, libc++, has all the headers it's implemented and provides the headers, but depending on the standard you're compiling with, it might have an empty body. That header might be empty. So it is physically on disk, but your compiler, depending on the flags you're compiling with, whether it's C++ 14 or 17, might not have that content. So you cannot use hasInclude for that. And this is important because you don't want a span-like thing that it's my span. You want it to have the same name and the same API, so that when the proper C++20 span becomes available for your toolchain, you can just swap the namespace or use the standard one, and it just works. You don't have to change anything in your code. So this is why you would bother doing this. But it's not straightforward, unfortunately, because they forgot to provide the feature test macro. I don't know what's your opinion on this little thing, a new kind of main. I saw this on the internet. I think somebody tweeted that. I don't remember exactly. And it basically combines two of my pet peeves into one glorious disaster. And this is because it looks attractive. It certainly is compact. But like most entry points, like main, you might expect some of those arguments to be passed to some POSIX function or some API that might expect a null terminated string. And mind you, string view is not a null terminated string. It might be, but it's not guaranteed to be. So beyond span, we do have good things coming. These are higher level abstractions. They come from the ranges proposal. And these are things that we're going to get in the future. Things like stride view, slice view, sliding view, cycle view, chunk view. We've seen this in other languages. Some of you might recognize some of these concepts from Haskell or other functional languages. So we're going to get higher level abstractions, but these are different things. Span is meant like an efficient low level solution for a common problem, that of formal or implicit ranges. These come as a higher level abstraction that can work over any kind of sequence, whether it's continuous or not. So these are different beasts, and we don't have them yet. I mentioned earlier, we're going to have coming down the line multi-dimensional array reference and owning multi-dimensional array. These are going to come later in the future, and they're all about defining data layout in memory, and they're useful for high-performance computing and graphics. But these are concerns for other talks, and they're probably going to come in C++23. My call to action to you would be to make your value types regular. The best regular types are those that model built-in types. Think int, think standard vector. So try to model things as close as possible and not to have any dependent preconditions. Try to make things that can make types that can be reasoned about without contextual information. So for non-owning reference types like string view and span, because we have those and we're going to see more of those, and maybe you're designing your own things like those, you need contextual information. We're working with them, and learn from the span story there that I just told, and try to restrict those types to be semi-regular to avoid confusion for your users, to meet the expectation. Make your types honest. Don't pretend it's regular and provide some weird behavior about comparing those types and assigning those values. Try to be honest. If the usage you are trying to impose on the users of your code looks weird, you better not provide it. So that's about the story of my span. Thank you very much.
Viktor Kira, everyone. Thank you. We're really out of time, but perhaps just a quick 1 or 2 questions from the audience. And again, the rule is the same as yesterday. So if you'd like to ask a question, please join us here downstairs and pop yours.
And if you're a little shy, you can always catch me on the hallways later too.
Yeah, absolutely.
Yeah.
Will you be staying later on?
Yeah,
okay.
I'm here all day, so you can catch me later too.
Hi, thank you for the talk.
Hi.
My colleagues and I always have argument whether types should have a default comparison operators, and I say that they shouldn't, because you should be explicit about like what kind of relation you want to model.
Yeah.
What is your thoughts on this?
Well, you're gonna be able to do that with the three-way comparison operator. So you can define an equal default spaceship operator starting with C++20. Whether that's a good thing for the type you're designing or not, you should be the judge of that. I wouldn't consider it a good universal practice to provide an equality. I think you should think about if an equality makes sense for your type.
But then, I mean, if the STL requires us to make regular types, they should have an equal operator. And is it good that we should always make our types regular then?
This is a different reformulations. Is it something that is desirable? All our types should be regular.
Okay.
Yeah, I'm a big fan of that.
Okay.
But I would admit that it's not possible for all types. For example, there are types that you're designing that are not actually values. So they provide some kind of functionality. They have data members, but they have functionality. They are actions that perform some transformation. So they don't model values. So for those kind of things, it would be weird if we would provide an equality for those kind of things. Like a class that manages some kind of state or performs some kind of action. That would not be a good candidate for a regular type. It could be, but it would be weird, because what does it mean to have a value of a type that has performed some actions? So it's not always possible. But for types that you designed that represent a value, that it's something that you can check for equality or you can assign it, then it better behave regularly. So
thank you very much.
It very much depends on the type. Yeah.
Thanks.
Yep.
Yeah, if I may, I think it goes along. It's more of a comment and asking for an opinion, but I think you did one reckless thing on one of your slides when you presented the mothership operator or the starship operator.
Yeah.
And on the when it returns 0, you have written or stated that it means that what are you comparing is equal / equivalent. And those are two different things semantically, and I don't think you can say that they are equivalent with that, because it's a starship operator. They go in 3, so they can only be equal. That's a semantic mismatch, in my opinion, and it resurfaced later on when there was trouble. And I think it's a trouble that all the scripting language have, like identity operator, triple equality.
Triple equality.
Yeah. So, do you think it's a good idea to say that when a spaceship operator returns 0, it means the objects are equivalent in terms of identity rather than only equal, without comparing their identity?
That's a difficult question.
Sorry, that's a math question, basically.
Yeah, I think it's a deeper question than that. Whether the equality should be considered like identity, it's tough. Think about providing such a comparator, for example, for a standard set or for a hash map. Or a hash set implementation. There are several good use cases where you're just very well do with just equivalence, and identity is not a good choice necessarily. So I would be very cautious about generalizing here, and that equality should imply identity everywhere, because there are good cases where you can have an equivalence relations, and it really makes sense for what you're comparing there. Think about, for example, comparing strings case insensitive, or comparing or building a hash map and just traversing and examining just an important part of the type you're actually storing, like maybe an identifier or a name field or something like that. So like a partial equality, and you consider that to be like this part of my object represents its identity in my with regards to my operation. So identity with regards to operation rather than identity as a whole. Like, are these two objects the same object in memory? So identity with regards to an operation rather than identity in terms of memory address or a locus in memory. So I would be very cautious to generalize there. For more things on the Spaceship Operator, I do encourage you to watch Jonathan Mueller's talk from CPPCon. It's very recent, and it goes really in depth. And I think it's very, very good.
I think we need to leave it at that. Thank you very much. Please join me in thanking Viktor Kira.
Thank you. Thank you.